So before coding up the dynamics of the simple harmonic motion, let's just look at what it is. Let's just revise what simple harmonic motion is. So in simple harmonic motion or a spring mass system, there is a spring with the constant k. Uh, the spring has an equilibrium line on which if the mass is kept, there is no force applied by the spring to the mass. But if it is moved by x distance on either side, um, the spring applies a force F shown in green on opposite to the direction in which the mass was moved. So let's say we have this mass m. It has been moved by x displacement. There is a force F. Let's try to write the equation of motions of the system. So the equation of motion is F is equal to minus kx uh, because F is applied in the opposite direction of displacement x. We can write this as mx double dot equal to minus kx, where x double dot represent double derivative of displacement x with respect to time. And this equation can be converted to the equation on the third line, x double dot plus k by m x equal to 0. And in terms of simple harmonic motion, it is written as x double dot plus omega square x equals to 0, where omega is square root of k divided by m. So this is the differential equation of a simple harmonic motion, and we want to get the function of x with respect to time so that we can simulate it or animate it in Python. So the thing is, if we solve this differential equation, it's a linear differential equation, so it's easy to solve. The solution comes out to be x as a function of time is equal to a cos x omega t plus phi, where a is an amplitude and phi is the phase angle. So these, if you give them, if we know these, this amplitude and phase angle, we can um, simulate the simple harmonic motion. So basically, the function that we plotted the sine x last time, here it is different. It has been replaced by a cos x cos omega t plus phi. There's one more important quantity in simple harmonic motion, which is time period. So time period is given by 2 pi by omega. So time period is basically the amount of time it takes the simple harmonic motion to complete one oscillation. So this is the simple mathematics in all the dynamics of simple harmonic motion. Now let's use this to code up the simulation or the animation of simple harmonic motion. So we are back to the Visual Studio Code. Let's make a new file. We call it shm animation.py. So shm means simple harmonic motion. So let's start coding in this. So just if we want to look at uh, previous animation, we imported the libraries, we wrote the functions, the dependent and independent variables, we opened the figure, we plotted, and then we ran this loop for animation, and then we close the plot. We'll use a um, similar framework for doing this. Let's just copy this import function. We don't need to write this again and again. Now let's write the parameters of uh, now let's write the parameters of the uh, simple harmonic oscillator. So basic parameters. I'm just writing so that it is code is readable. So let's start with mass. So we keep it 1 kg. K is the spring constant. We'll also keep it. Let's keep it 10. Now we'll write amplitude, and let's just keep it to 1 again. Now omega. So we saw omega, the angular frequency of SHM, was given by uh, under root of k by m. So the way we use square root function, we can take help of this sqrt function from numpy. So this gives us the square root of the argument, and this is I think mass. So k by mass is omega, angular frequency. Then phi is the phase angle. So let's keep it 0 for now. We can change it later when we are analyzing the animation. And then time period. Time period was given by 2 into pi slash divided by omega. So the thing is pi is um, not by default present in Python. So what you can do is either you can use some approximate value of pi, or and numpy gives you the option of using pi np dot as np dot pi. Okay, so we are using that. Now let's define our um, dependent variable or independent variable, sorry. So t is np dot linspace, uh, let's call it 0 to, yeah, so we should decide some maximum time for which we want to run the animation. So t max we can define it as, let's say, 2 into time period. So it will run for 2 oscillations and then it will stop. So t max, and we can start with let's say 100 points. All right. So yeah, so this is we have already defined the independent variable. Now let's define the dependent variable, which is given by x. So as we saw in that equation, uh, it is given an amplitude times cos, np dot cos, into omega into t plus phi. So this is our dependent variable. All right. So we can write this independent and dependent variables just to make the code readable. Okay, now we have this. So now we have our dependent and independent variables. Now let's just plot the first frame. Okay, we'll do as we did in the previous video, in our previous animation file, that we'll first plot the first frame and then use the loop to iterate it. So let's plot the mass first. So um so we don't want to plot the t versus x graph. Remember, we want to plot the the position graph, and each successive frame is the time. So time is in is moving when animation is moving, and not, it's not a graph. So what I'm saying is, let's, in the first frame, the mass will be at x 0 and y coordinate 0. So at this point the mass will be, so I'm not using time here because um, time will be shown in terms of animation, right? So yeah, so um, this is the plot. Let's select its color and style. So RO. So what this will do is basically it will give it a red color, and it will give it a round shape. Okay. Let's run this and see what do we get. Okay, again, I think we'll have to pause it for a second. So plot.pasc, pause. Or let's say 2 seconds, and plot dot close. Okay, now let's run it. So yeah, so at 1 there is a round dot. So we plotted the mass, the first frame of the mass itself. Now let's plot the first frame of the spring. So the way we'll represent spring will be using a line. Okay. So how do we plot a line using in plot function? So the way we plot it is we give it a list of points. So for example, you can give it, let's give it some random point to see how it works. So 0 comma 10 or 0 comma 2 and 0 comma 3, and let's just give it a color B and straight line B and dash. Okay, so what this will do is uh, it will plot a line from 0 comma 0 to 2 comma 3. So what this means is the first list is the list of x's that it will plot, and the second list is the list of y's that it has to plot. So basically it will give a line from 0 comma 0 to 2 comma 3. Okay, let's see what it prints. Yeah, so it gave 0 comma 0 to let's just increase this pause for some time, we'll reduce it later. Yeah, so we have a dot at 1 comma 0 and a line from 0 comma 0 to 2 comma 3. All right, but we want this string for 0 comma 0 to 1 comma 0. All right, so let's do that. We want the point from 0 comma 0 comma 0 to x0, y coordinate should be 0. So because simple harmonic motion is not moving in y, it's only moving in x direction. Okay, now let's run this plot and see. Yeah, so now we have this spring. Blue is representing spring and red is representing the mass. Okay, yeah, so this is the first frame of the plot. Now let's iterate it for I in range len of t, plot this and one I. Okay, now we also know that we have to use um, pause and remove function as we used previously. Otherwise, it will it will plot all the frames which we do not want. We want to remove the previous frame and plot the next frame. Okay, so we'll give them temporary names. So mass plot and spring plot. Okay, now let's pause for some time. So plt dot pause, let's say 0.02, and we'll remove them. Mass plt dot remove and spring plt dot remove. Okay, and we'll reduce this final pause to, let's say, 1 second. Let's just see how it behaves. So this should work. Okay, so um, so it it plotted for some time. Let's increase the time period for some time. Let's say 5 time periods, and then we'll see. Okay, so one thing that you might have noticed that in the first frame, uh, the frame becomes bigger. So let's just we can also like while the simple harmonic motion is being moved on the left side, and we do not have enough space on the plot, but it like it pushes the plot to, so that now the simple harmonic motion plot can be on the whole screen. We can fix that by setting the limit of the x and y axis. So you can do that as well. So let's fix the limits. So plt dot x lim function we can use, and similarly plt dot y lim function you can use. So how much do we want to fix? Let's say our amplitude is 1, so amplitude times 1.5. So the way it works is it has to first give the lower limit, so 1.5 into amplitude to minus 1.5 into amplitude to 1.5 into amplitude. Same with y, but because there is no motion in y, we can just simply say 1.5 comma 1.5, sorry, minus 1.5 comma 1.5. So this should fix that initial problem, that the frame itself becomes bigger. It will not happen now. Let's see how it behaves. Okay, so as you saw initially, there was um, no increment, like frame was not changing at all. So that is better. The second thing is this pause is of some arbitrary value. To make it feel real, this pause should be the time difference between two successive points we have. All right. So what is the time difference that we want? Let's call that small time dt, and it can be given by t1 minus t0. Note that all the successive time differences are same because we have uh, spaced them equally. So this lin spaces these 100 points equally. Okay. So now this is the instant of time. We can, instead of 0.02, we can use dt. All right. So now let's run this code and let's see what difference we see. You can see the spring mass is oscillating slowly compared to previously. So this is now real time. Now one more thing that I want to change is let's um, change this max time period to 2 and see if so we saw previously that if we change this from 2 to 5, it becomes really fast. This change, however, should automatically fix dt in such a way that uh, it does not alter the speed of the animation. It follows the physics. So let's try to run it now. So the speed is same, it's just that it will now run for 2 time periods. Okay. So at the end, you saw that there is a time gap in which the plot becomes blank. I think it's because of this plot pause at 1 second. So I don't think we require this, so we'll comment it and just run it once again. Okay, so yeah, so that's how we can animate something with physics. Here you saw that we had we had some differential equation of simple harmonic motion. We solved it analytically, got the value of x as a function of time, and then plotted it. Similarly, you can plot things which you cannot find analytical solutions of X. So, for example, for complicated systems, sometimes you cannot find analytical solution. You cannot find X as a function of time sometimes, but you can find the solution numerically. So there are some algorithms which help you find numerical solutions to differential equations. And once you get this xt, you can again use this similar concept to animate them as well. I'm not going to cover the how to find a solution of a differential equation, but we'll do that in successive lectures. But till now, you can practice these methods of plots and animations and play around with it to get more familiar with it. So see you in the next lecture. Till then, thank you.